Hi everyone. Like Fela said, my name's Anubhav. I'm doing my master's in CS at Waterloo right now, and I was here for my undergrad too. So I was in the co-op program, so I have done quite a few interviews, and with those interviews came a lot of leet code grinding. At some point, I realized that the leet code grinding wasn't helping because they were asking me questions like, how do I design a system, or explain this hard decision that you had to make in the past. One question that really stuck with me was the one that I'm going to present today, which is what happens when you type google.ca into your web browser and hit enter? And the short answer is a whole lot. I'm going to go through it in what might seem like excruciating detail to you, but I promise it's barely scratching the surface of what actually happens. Okay, let's get started. So the first thing that happens is you press the G key. If you have a cheapo keyboard like mine, you probably have underneath your keys a plastic membrane full of these rubber domes. When you press the key, the carbon center in the middle of this key will complete a circuit, and the keyboard controller detects that as a key press. If you have a more expensive mechanical keyboard, the process is still mostly the same. You're still completing a circuit, except you get some extra clicky feedback and maybe some dopamine in your brain. If you're really fancy, then your keyboard might have switches that look like this. These are optical switches, and you can see when the key goes down, the laser is able to hit the sensor on one side. And again, that goes to the keyboard microcontroller, which is this thing, almost certainly this exact chip. And the keyboard microcontroller sees, well, it doesn't exactly see a key was pressed. It doesn't see that G was pressed. In fact, it sees something like this. It gets a signal, but the signal can be noisy. And to denoise it, it does something called debouncing. Debouncing is when it turns this essentially spiky graph into a flat 0 and then a flat 1, and it can use that to detect what key was pressed. Once it knows what key was pressed, it sends that and any modifier keys that you might have pressed, like let's say you pressed the shift key or you pressed control with it, it sends those to the computer through whatever interface you have. In my case, it's a USB. And your computer will get it. At that point, your USB driver will send an interrupt to your computer, which is essentially waving a big red flag to the kernel saying, hey, operating system, please pay attention to the fact that I pressed the G key. So the operating system, the kernel pays attention to it. Then it goes through a bunch of layers of software, like a lot of code, and eventually it gets to Chrome. When it gets to Chrome, you see something like this. So how did we get here? After Chrome gets to G, it checks a list of sites that you've already visited and things that you've searched for in the past to try to auto-complete what you're looking for. So after you get this, let's say you press enter, and same thing happens that just happened on the previous slide, but now Chrome has some work to do. It knows that you want google.ca, but what is google.ca? Is it a URL? Is it a search term? It looks like a URL, but you might notice if you actually go to google.ca and you click on the top that there's an https://www. So the last part, Google assumes this part, the www. But how does it know we want HTTPS, where the S stands for secure HTTP, instead of just normal HTTP? Well, to do that, the browser checks what's called its HSTS list, which stands for HTTP Strict Transport Security. Pretty much, this is a list of sites that comes pre-packaged with your browser when you download Chrome that says that the site only wants to be contacted over an encrypted channel. And every big site every big site that I checked on the HSTS list for Chrome was there, except for like Piazza. And you should see a lock symbol here. And where is google.ca? To find google.ca, this is just a domain name. We need an address. Imagine in the real world, you want to find someone, you need their address. So an address on the internet called an IP address uniquely identifies the server that we want to talk to. The first place you might want to check to figure out what the address of Google's server is Chrome. So you might ask your browser cache, hey, Chrome, do you know the IP address of google.ca? And it might say no, it might say yes, but let's assume for now it says no. If it says no, the next thing you do is you go to the operating system. You go to Windows. So Windows, do you know the IP address of google.ca? If Windows also says no, then we have to contact a higher power, which in this case, in my case, it's Rogers. So we have to contact Rogers. If you've ever called Rogers customer support, you know that we're not about to call them because we want google.ca to load within the hour. So to translate the domain name google.ca into an IP address, Rogers maintains what's called a DNS server, a domain name system server, which maps from the domain name Google to the IP address. So how do we send Rogers our request for getting the IP address of google.ca? So the first thing we're going to do is we're going to take our data and we're going to wrap it in a bunch of routing information that's going to let us send it to Rogers. It's like the envelope we had on the last slide, but instead of sending one envelope, we're going to send a lot of nested envelopes. By the way, everything on this slide applies to sending things across the internet in general. It's not just for sending things to Rogers. So the first thing we add to our data is the port that we want to send it to on Rogers's machine. This is like a docking point for our request. The next thing we add is our IP address, Rogers' server's IP address, and a field which is called time to live. And I'm going to explain this in a bit more detail in a bit. The last thing we add is our MAC address, which is a manufacturer-assigned unique number for every electronic device. Now that we have our very big envelope, we're going to need to convert our envelope, which is zeros and ones, into electrical signals so it can be sent out to Rogers. The way that this is done is using a device called a modem, which does two tasks. The first is called modulation, and the second is called demodulation. Modulation is converting from the zeros and ones that represent our big nested envelope of data into electrical signals, and demodulation is converting it back. So once we have our electrical signals, they're sent over the network through maybe fiber optic or maybe Ethernet or maybe Wi-Fi. If you own a satellite, I guess you could send it through your satellite as well. And it goes through multiple hops, so maybe multiple nodes on the internet. These nodes act like post offices for our nested envelope and ensure that it gets to the eventual end spot which we want, which is Rogers. So each node, when it gets our nested envelope, is going to look at it and figure out where it should send it next. It also reduces the time to live field, which we saw on the previous slide was 10 by 1, and it sends it to the next hop. The reason it does that is because it wants to, in case a network node fails, in case this router decides that instead of sending our envelope onto Rogers, it'll just send it back to us. We don't want our packet, our envelope just infinitely circulating in the internet. We want it to eventually die out. So in this case, after 10 jumps, it'll die out. Okay, so once we get to Rogers, we have to, they'll look at our packet and they'll see that we want the IP address of google.ca. If they don't have it, then they'll check their IP table and they see it's not there, and they'll return null. So if we can't find it, we'll see a site that looks something like this on Chrome, which is a sad face. But if it can find it, then we'll get an IP address like we see is here for Facebook. Okay, but remember that Google wanted us to contact them over an encrypted channel. So the next thing we have to do is set up an encrypted channel. So we have to set up our encrypted data so that we can protect it from hackers like these on the internet. To do that, the first thing we do is we send the server a message which says, these are the types of encryption that I support, and this is the type of cipher that I support, because not every server supports every type of cipher and every type of encryption. So the server will respond back, let's use ECC as elliptic curve cryptography, and we'll use the only block cipher you gave me, and it'll also send back a certificate. The certificate is essentially the Google server saying, I am Google, and it's verified by someone that my browser trusts. So when my browser gets the certificate back, it knows that we're talking to the real Google. The next thing we do is we generate what's called a secret key. So the secret key is going to let us encrypt all our future messages. But how do we send it to Google? We can't send it just over the wire, because then someone snooping on our connection might be able to pull out the secret key, and we don't want that. Then they could decrypt our encrypted messages. Instead, what we do is we encrypt the secret key in a way that only Google's server can decode it, and we send that encrypted version to them. I'm glossing over details here, but if you want to understand this, you should definitely take CO 487 at Waterloo. It's applied cryptography. It's a great course. So at this point, the Google server has our secret key, and we have the secret key, and we're ready to send as many encrypted messages as we want. I'm only going to go over the first of the encrypted messages. It's the most important one here. This is the GET request that we send to Google. So it's pretty simple. Here on the right is the request, and let's break it down. So HTTP 1.1 is the protocol. it tells Google server how the data that we're going to send it and receive from it should be formatted. And the protocol includes some verbs which allow us to read data or write data. In this case, we want to read the Google homepage. So get for read and the / for the Google homepage. And the host is google.ca because, well, we're sending our request to google.ca. We also have another field here called connection close, which means that once the server is done sending us whatever data it means to send us, it's free to close the connection. We don't need to keep it around. When Google gets the request, well, we don't exactly know what they do because Google's code is private. They don't really just release it to the world, but we can make a decent guess based on what other servers do. So it probably extracts the verb that we sent it. So we want to get the homepage / at google.ca. And then it does some processing. So it says, are the gets allowed on google.ca? And then it checks that we are allowed to get the google.ca page. That is, it's not an encrypted page. It's not someone's passwords or anything like that. After that, it ships all the data together and it sends it back to us. And if everything went well, we should see a response code of 200, which means everything was okay, and we should get some data back with it too. Once we get it back, the response should go through the network, it'll go through our modem again, it'll go through the operating system, and finally it'll reach our browser. And here's where the fun begins, because browsers are incredibly complex tools. Chrome itself is around 35 million lines of code as of right now. And yeah, so when a browser gets this HTML, this is what it might get from the Google server. It first does two things. The first thing it does is it converts it into a structured format like this. This tree is called a DOM tree, and we're going to see a bit more of this on the next slide. And it's going to use this to render into our final page, which should look like this. Yeah. So let's talk about the first part, going from HTML into the DOM tree. There's two main challenges that browsers deal with when they're parsing HTML into DOM trees. The first is that they have to handle broken HTML according to the Internet Engineering Task Force. So if the server sends us complete garbage HTML, then there's a specification on how Google is supposed to try its best to display the page, how Chrome is supposed to try its best to display the page. Luckily, google.ca is a nice website. It usually doesn't send us garbage data. So the bigger problem that our browser has to deal with is JavaScript. So these nodes here, these yellow and blue nodes, the yellow nodes here represent text on our page, and the blue nodes represent content structure like the headings or titles, but they can also represent other things. For example, they can represent code. And when our browser parser sees the code tag, it has to process the code and run the code. The complicated part here is that if one of those code tags modifies the original HTML document, then our tree is changed, and we may have new code tags to run. So the flow looks kind of like this. You don't really need to pay too much attention to the content of these boxes, but pay attention to this loop here. This is essentially JavaScript running, modifying our document, and then adding more JavaScript, which has to be reparsed and re-added into our document. Eventually, the browser stabilizes and it gets some sort of DOM tree like this, and we can move on to the next step, which is rendering. So the next step is going from this DOM tree, which is this tree on the left, to an actual page that we see. Along with the HTML that it got from the server, the browser also received some CSS files from Google, which are like a rule book for how it should display the elements on the page. But it's a really high level rule book. It's not like, the rule book says stuff like, don't have the text leave this box. But it doesn't tell the browser how to lay out the text to leave the box. It doesn't tell the browser how big the box should be. And it's the browser's job to do that. That task is called layout. And essentially the browser has to figure out that in this case, it needs to make the box a bit bigger and it needs to break the line text. It needs to line break the text here. After that, after the layout, there's also the problem of painting. So if a user asked, for example, for a circle and a square to be drawn on the exact same spot, well, the browser can't do that. So it has to decide which one it draws first. And this can all be made more complicated by the fact that this whole time JavaScript might be running in the background, updating the DOM and saying, hey, maybe we want a triangle on top of this too. maybe we want to add some extra text in here, and that'll make our box have to be bigger. And the browser has to deal with this. It has to move other things around. It has to all happen at 60 frames per second. Otherwise, people on the internet get mad. And it's a very hard task. So sometimes we need the GPU to help us. But even with that, it's an extremely like monumental feat that the browser is able to accomplish this at 60 frames per second. After that, we've sent the request out to Google. We got a response back. We did the parsing. We did the rendering. Are we done? For now, yes, just because this talk has to be constrained to 15 minutes. But I hope that now that I've gone through this, you appreciate the complexity of the question, from different types of keyboards to DNS servers maybe not having the IP address that we want, to browsers having to deal with our incredibly complex and ever-changing demands. There is a lot more complexity to this problem than you originally see. Yeah, but I also want you to remember that it doesn't matter so much that you remember everything that I showed you today in detail. I'd rather have you take away an appreciation for the complexity behind what might seem like very simple systems. Oh, and if this ever comes up in an interview, I'm expecting all of you to ace the question. So yeah, that's it for me. This talk was mostly stolen from Alex Gaynor's GitHub. It's a collaborative effort which tries to explain what happens when you type google.com into Chrome and you press enter in as much detail as possible. And there's a lot of things that I didn't discuss that are in that GitHub post. And the browser parsing and the rendering descriptions are from Mariko Kosaka's blog at Google. It's actually an amazing blog series, and you should definitely read all 4 parts of it. Okay, I think that's it. I'm going to see if I can switch back and stop presenting now. Yeah.
Thank you. That was so good. I feel a little bit smarter. And everyone has questions, send them in the Q&A section or the chat right now. We'll wait like a minute for questions just to see if there's like a lag. The chat's very nice. Aww.
Oh, yeah. So DOM stands for Document Object Model. So it's the HTML document. What are the objects in it? Yeah. Okay, no questions.
Yeah, we're getting a lot of claps though. That means the presentation was so clear. It was beautiful. Thank you, Anubhav. Okay, and now we're gonna go on. Oh wait, one question. Oh no.
I got a question this one. What's the most complex part of the system? It really depends what you mean by complex. First, I'm not an expert on this, so a little bit of this is I'm not super qualified to say, but I would say it feels like there's one really good way to do the network stuff, so we've kind of figured that out. But I would say the browser part for sure, like the rendering and the parsing. Quantum effects in the CPU design. Yeah, I mean, if you want to go deep into it, then this, I guess, relies on everything in CS. So yeah, whatever the most complex CS topic you can think of is that.